Welcome back. It's Professor Boudreau at Snow College. We're going to do section 8.3 today, talking about doing a hypothesis test about a claim for a population mean. So the first thing we want to do is know and verify the requirements for a hypothesis test of a mean, and then we will perform and interpret the hypothesis test for a mean together. And just as a quick review of our concept map here, so we're doing a hypothesis test on a population mean. And remember, just like we did in chapter 7 with confidence intervals, the population mean branches out into two branches depending on if we know the population standard deviation or not. If we know the population standard deviation, then we use the z distribution. If we don't, we use the sample standard deviation as a stand-in, and we need to use, therefore, the t distribution because of the extra error introduced. So we will follow this process here. So the first one we'll look at, we'll deal with when we know the population standard deviation, but then what happens most times in real life is when we don't. But I do want to show you a situation where we do know the population standard deviation. So as usual, our requirements are to check if we do know the population standard deviation, it has to be known. Then, as always, we need a random sample, and we need n to be greater than or equal to 30, or the original population to be normally distributed. And once again, that's our good friend central limit theorem, why we had to do chapter 6. One of the few cases where we do know the actual population standard deviation is the Wechsler IQ test. They are set up so that we have a mean of 100 and a standard deviation of 15, and IQ scores are normally distributed. A random sample of 13 Snow College professors had a mean of 110.4. Does this indicate that Snow College professors have an average IQ score that is higher than the national average? And this time, we're going to change it up a little bit, and I'm going to give you a 1% level of significance for alpha. So let's go ahead and do our requirement check. Did we know the population standard deviation? Yes, and it was 15. Maybe this is a good time to take a second here and look at what we've got. So let's go back through our problem. Let's notice that we are normally distributed. Okay. We had a mean of 100, but we've also had another mean of 110.4. So we need to make sure we know which is which. So this 100 was the mean from all IQ scores. So we're going to write mu equals 100 because that's the population mean. This mean of 110.4 came from a, read the problem, read the sentence, the sample. So our sample mean is 110.4. Our population standard deviation is 15. And our sample standard deviation, we don't have the sample standard deviation because we don't need to know it because we know the population standard deviation. So were we a random sample? Yes. Let's write that down over here. Or on an activity, you could circle it. But on a test, you'll probably have to write it down and verify. We only had 13 for our sample size. Okay, so that's not big enough unless the original population is normally distributed as it was. So we're going to circle this and random, so we have met our requirement checks. We're cleared for takeoff. So let's write down our null and alternate hypotheses. The claim that we're putting on trial is that the Snow College professors have an average IQ score that is higher than the national average. So if we take, and instead of asking just 13 Snow College faculty, we ask all Snow College faculty, have them take the IQ test. What would their average be? We're checking to see if it would be over 100. So our null hypothesis would be mu equals 100. But if you want to get really technical, you could write mu is less than or equal to 100. However, the claim we're putting on trial, our alternate hypothesis is that the mu is greater than 100. So this would be a right-tailed test. And if we do the traditional method, we need to draw our picture here. And we'll draw our z distribution. And we want to remember that the alpha, our level of significance, was 0.01. So we want to have 1% of the area in the right tail. And since we're using the z distribution, we're going to use our wonderful orange z table. And to get 1% in the right on a left-handed distribution, we need to find 99% to the left. So I need to find 99% or as close to it as I can get. This is as close as I can get. So the z-score that will do that is 2.33. So our critical value is 2.33. We'll think of this as our beyond reasonable doubt. And we'll shade to the right. And note that this gives me, in purple, 1% of the area under the curve. Now, if we land there, then we will reject H0, come back with a guilty verdict, and conclude that we do have enough evidence to say that the average IQ score is over 100 for Snow College professors. But we need to actually listen to the evidence. So let's find the test statistic, and let's turn on our calculator here. So let's do some parentheses. X bar, which was 110.4, minus the population mean of 100. And we're going to divide by sigma, which was 15, divided by square root of our sample size, which was 13. Good thing we wrote that all down. And we do have an operation in the bottom, so we do need some parentheses on top and bottom. And if we do that, we will get a test statistic of, rounded to 2 decimal places, 2.50. So our test statistic of 2.50, if we graph that, that landed in the critical region. Therefore, since we landed in the critical region, we will, like we said, reject H0. So there is enough evidence to conclude that the average IQ score of all Snow College professors is greater than 100. Okay, hope that's made sense. Let's go ahead and see what we would do if we were to do the p-value method. To save just a minute of video time, I'm going to go ahead and do the same stuff here. We'd still have a right-tailed test. We'd still have everything else. We'd still get, oddly enough, the same test statistic, but now we need to compute the p-value. And remembering that this is a right-tailed test with a test statistic of 2.50, if we look up 2.50 on our table, the area to the left is 0.9938. So the area to the right would be 1 minus that. So our p-value would be 1 minus 0.9938, which is 0.0062. And if we compare our p-value of 0.0062 to our alpha of 0.01, we see that the p-value is less than alpha. And as we've talked, if the p is low, then the null must go. So we will get, once again, the exact same conclusion we will reject H0. There is enough evidence to conclude that the average IQ score for Snow College professors is greater than 100. We'll pause right there and come back in the next video.